I am happy to welcome you all to this module. The title of the module is the matrix equation Ax is equal to B and the solution set of linear system. In this section, we learn how to express the linear system of the equation in a matrix equation Ax is equal to B. Then we discuss the two types of matrix equation called homogeneous system and non-homogeneous system. By expressing the linear system in matrix equation, we learn to solve the system also. The matrix equation Ax is equal to B, that is what we are going to learn now. We are going to learn how to represent the system of linear equation by matrix equation. The general system of m linear equations with n unknowns is given by the equation. System of equation is displayed on the screen, that is what we have discussed earlier. And the system that is equivalent to the matrix equation. The matrix is also displayed on the screen. You can see here A represents A is a matrix with has entries Aij's, and that is called as the coefficient matrix. These are all already discussed in the previous module. And X is a matrix with entries Xj and B is a matrix with entries Bi's and are called as column vectors of variables and constants respectively. This matrix equation can be written simply as Ax is equal to B. Both the system of linear equation and the corresponding matrix equation is equivalent, means any solution of the linear system satisfies matrix equation and vice versa. Consider the example. So, this example that is the system of equations were already discussed in the previous module. Consider that. The corresponding matrix equation is also given, that is on the screen. You can see now. The solution is x1 is equal to 29, x2 is equal to 16, x3 is 3. We solved the system in the previous module and we obtained the solution, and the solution set is 29, 16, 3. We denote that by u is the solution of the system. So, now we are going to see existence of solution. When do we have the solution for the corresponding system of equation? The definition Ax is equal to B leads directly to the following fact. The equation Ax is equal to B has a solution if and only if B is a linear combination of the columns of A. Same as the system of linear equations, a matrix equation can have either no solution or exactly one solution, namely unique solution, or infinitely many solutions. Since both of them are equivalent, the matrix equation is said to be consistent if it has one or more solutions, and it is said to be inconsistent if it has no solution. An example is on the screen. We shall consider a matrix A and B. So, is the equation Ax is equal to B consistent for all possible B1, B2, B3? That is the question for us, and we have solved that. First, we are going to row reduce the matrix A, and the row reduce form is there on the screen. So, these operations we have already discussed. The third entry in the augmented column is B3 minus 2B1. The equation Ax is equal to B is not consistent for every B because some choices of B can make B3 minus 2B1 to be 0. The equation Ax is equal to B fails to be consistent for all B because the echelon form has A has a row of zeros. The echelon matrix in the above example provides a description of all B for which the equation Ax is equal to B is consistent. The entries in B must satisfy B3 minus 2B1 is equal to 0. Let us see a theorem. The statement of the theorem is, let A be an m by n matrix, then the following statements are equivalent. That is, for a particular A, either all statements are true or they are all false. First statement, for each B in R power m, the equation Ax is equal to B has a solution. Second statement, each B in R power m is a linear combination of the columns of A. Third statement, the columns of A span R power m. And the fourth statement says A has a pivot position in every row. So, the columns of A span R power m means every element of R power m can be written as a linear combination of column vectors of A. This theorem is about a coefficient matrix, not about an augmented matrix. If an augmented matrix AB has a pivot position in every row, then the equation Ax is equal to B may or may not be consistent. So, how can we compute Ax now? We are going to see that with an example. So, here a matrix is given and the set of unknowns x1, x2, x3 with the column matrix also given. We are going to compute Ax is equal to B. First Ax, we shall see a solution now. So, here consider minus 1, 3, 11, that is the matrix that is given to you, and the column matrix, and this is just a simple multiplication. You will have x1 multiplied by minus 1, 19 minus 2, and plus x2 minus 3 minus 7 0 plus x3 11 5 7, and at last you have this matrix with it is again a column matrix, you can see, and in the first entry of the column matrix is minus x1 plus 3x2 plus 11x3, second entry is 19x1 minus 7x2 plus 5x3, third one is minus 2x1 plus 7x3. So, this is how we compute Ax, and this is just a normal matrix multiplication method, you can easily see compute. Now, we shall see a theorem, that is here A is an M by N matrix and we have two vectors, namely u and v, taken from R power n, and C here we are considering a scalar. So, altogether we have a matrix, we have two vectors and we have a scalar. Now, we are going to prove these two properties. The first one is A multiplied by u plus v will be equivalent to AU plus AV, that is linear property, and then the second one is also A multiplied by Cu is equal to C multiplied by AU. So, this is what we are going to prove now. In order to prove the first part, I am considering A multiplied by u plus v. You have to note A is a matrix, u and v are vectors taken from R power n. Therefore, u plus v is also a vector in the same field R power n. Now, so this A, for our convenience, I have taken my n to be 4. Therefore, I will be having only R power 4. So, this A of u plus v can be written in the form of A1, A2, A3, A4. So, here you can see it is an M by N matrix. For our convenience, we have taken this n to be 4. Therefore, we have M by 4 matrix, which means that we have 4 columns, and this A1 is this is a column vector. So, we have A1 and A2, A3, A4 representing its corresponding column, and we have this u plus v, this is again u1 plus v1, u2 plus v2, u3 plus v3, u4 plus v4 is a 4 by 1 matrix. So, now if you multiply it, you will have this one u1 plus v1 a1 plus u2 plus v2 a2 plus u3 plus v3 a3 plus u4 plus v4 a4, and you can again write this as, so this way of writing is possible here. You can write in this form of u1 a1 plus u2 a2 plus u3 a3 plus u4 a4 plus v1 a1 plus v2 a2 plus v3 a3 plus v4 a4, and finally when you look at here, you can simply write this as A multiplied by the column vector u, and then here this is A multiplied by the vector v. So, at last we are able to prove A multiplied by u plus v is equivalent to AU plus AV, and the next one is A multiplied by Cu is equal to C multiplied by AU. So, here A is a matrix, C is a scalar, U is a vector. So, that is what we are going to prove now. So, here A, as I told you earlier, this A can be written in this way, and for our convenience we have taken n to be 4. So, you can follow the same procedure in order to prove for general n also. So, this Cu I have written as Cu1, Cu2, Cu3, Cu4, this is just a representation, and this is how we usually represent. So, now, so if you do this operation, you have C multiplied by u1 a1 plus Cu2 a2 plus Cu3 a3 plus Cu4 a4, and after that what you can do, you can actually take C outside as C is a scalar. If you take C outside, you have C multiplied by u1 a1 plus u2 a2 plus u3 a3 plus u4 a4. What is that? That is nothing but AU. So, at last we are able to prove A multiplied by Cu is equivalent to C multiplied by Au. So, from this theorem we have proved the linear property of addition and scalar multiplication, and that is a matrix multiplied by the addition of two column vectors can be split and write, that is A of u plus v is equal to Au plus Av, and scalar multiplication A of Cu is equal to C of Au. Now, we shall see about homogeneous linear systems. A system of linear equations is said to be homogeneous if it is of the form Ax is equal to 0, that is all the constants are equal to 0, where A is an m by n matrix and 0 is the 0 vector in R power m. Such a system Ax is equal to 0 always has a solution, namely x is equal to 0, the vector called the trivial solution. Now, the question is whether this system has a non-trivial solution or not. So, that is the existence and uniqueness theorem leads immediately to the following fact that the homogeneous equation Ax is equal to 0 has a non-trivial solution if and only if the equation has at least one free variable. We shall see an example now. This is just an example. Here you can see we have a system of equations in 3 unknowns and we have 3 equations. As you can see, all the constants are 0, that is 0, 0, 0. So, this is a homogeneous system of equations. Now, we are going to solve this equation. So, as we have seen now, this equation will always have trivial solution, that is x1 is equal to 0, x2 is equal to 0, x3 is equal to 0. If we substitute 0, 0, 0, all the equations will get satisfied. Therefore, 0, 0, 0 is a solution. Therefore, there is no possibility for the system to be inconsistent because it always have a solution. Now, the question is, does it have a non-trivial solution? That is also we have seen it will have non-trivial solution if and only if it has a free variable. So, now we are going to solve it using the earlier method that we have solved using augmented matrix. We are going to see whether it has a free variable or not and what kind of solution does it have. Now, we are going to form an augmented matrix here. You can see we have A0. This A, we usually write AB. Now, all the B's have become 0. We are denoting this by A0. This is just a matrix, augmented matrix M, and I have written all the coefficients 4, 3, minus 2 and this is 0, minus 4, minus 1, 2, 0, 8, minus 1, 4, 0. So, this is what augmented matrix. Now, I am going to try to bring it into an echelon form by doing some row operations. So, now this is the first operation I have done. I have changed this R2 to be R2 plus R1, that is I have added R2 and R1 together and I have changed this R2. The first entry, the first row remains as such 4, 3, minus 2, 0, and then this entry minus 4, what I am going to do, I am going to add with the first row, right. Therefore, minus 4 plus 4 is 0, minus 1 plus 3 is 2, and then 2 minus 2 is 0. 0 plus 0 is 0. Therefore, this row I am getting. And what I am going to do in the next step, you can do all the steps in simultaneously, or you can do one step, form a matrix and do another step. So, now for the R3, that is the R3, what I am going to do, I am going to have this R3 and I am going to subtract it from 2R1, that is R3 minus 2R1, I am going to change that. Now, listen, so this is 8. 8 minus 2 multiplied by 4, 8 minus 8, that is 0, and 1 minus 2 multiplied by 3, 1 minus 2 multiplied by 3 is 1 minus 6, that will give me minus 5, and similarly 4 I have minus 2 multiplied by R1, that will have 0 and 0, here also I have 0, 0, 0, 0. So, after doing all the elementary operations I can apply, I am getting this equivalent form, that is this echelon form, where you can see in the last row I am getting 0 0 0 0. So now, which means this particular row corresponds, says that my variable x3 is a free variable, and as we have already seen, so if you have at least one free variable, then your homogeneous system of equation will have a non-trivial solution. Therefore, definitely it has a non-trivial solution. You can see it clearly here. So, I have written this as 1 0 minus 2 minus 1 by 2 0 1 0 0 0 0 x1 x2 x3 0 0 0, and after doing the stuffs you have x1 is equal to minus 1 by 2 x3, x2 0 and x3 is free variable, meaning that if you assign a value to x3, corresponding to that value will have values for x1 and x2, that is called as a system of solutions. So, now I have, if I assign x3 is equal to 1, corresponding to that you have x1 to be 1 by 2 and x2 is again 0, and here since x2 is 0, no matter what the value of x3, x2 will always remain 0. Therefore, there is a change only in x3. So, now since this has a free variable, it has a solution, and one of its solution is 1 by 2 0 1. Yeah, so we are able to solve this homogeneous system, a linear system for in fact. So, now let us move towards another problem where we are gonna deal with non-homogeneous system of equations, and we are gonna try to find the solution of that. Now, we shall see about the solutions of non-homogeneous systems. A system of linear equations is said to be non-homogeneous if it is of the form Ax is equal to b, where b is not equal to 0. When a non-homogeneous linear system has many solutions, the general solution can be written as a vector form of one vector plus an arbitrary linear combination of vectors that satisfy the corresponding homogeneous system. Let us see a theorem. Theorem states, let V be a particular solution of Ax equal to b and W be the general solution of Ax equal to 0. Then V plus W is the general solution of Ax is equal to b. We shall see an example now. Here, this is a matrix A 1 3 1 minus 4 minus 9 2 0 minus 3 minus 6 and b is equal to 1 minus 1 minus 3. As you have already assumed, this corresponds to a system of non-homogeneous equations, that is with the constant terms to be equivalent to 1 minus 1 minus 3, and this is their corresponding coefficient matrix. Now, if we have to form the augmented matrix, that is denoted by A comma B, that is equal to M, associated with this A, what we are going to do? We are going to add a constant matrix, that is 1 minus 1 3 minus 3, that is a column, a vector corresponding to the constants of the non-homogeneous system. Now, as usual, we have to form or we have to apply some row operations in order to reduce the augmented matrix in an echelon form. So, now I have applied a series of row operations, and I haven't mentioned any operation because you can do your own operations, not necessarily have to follow the operation that is done here, but the strategy is, the objective is at last you have to get an echelon form. So, that is you have to reduce the matrix. So, now I am able to find an equivalent echelon form, and then if I have to write in a way that Ax equal to b, I am getting again here x3 to be a free variable. So, I have x1 to be equal to 5 x3 minus 2 and x2 is equal to 1 minus 2 x3, and x3 here is still a free variable, meaning that if you change the value of x3 corresponding to x3, you have the value of x1 and x2. So, if you choose x3 is equal to 1, corresponding to that one you have a solution. If you choose x3 is equal to 2, then corresponding to 2 you have another set of solution. So, now here what we are going to do is, we are going to find the general solution of the given homogeneous equations. So, this can be written as the capital X is small x is equal to x1, x2, x3. This is if you have to find the general solution, what you have to do as per theorem that we have stated, how to find a particular solution and the particular solution plus the addition of the vector that you have obtained for the general, as a general solution of the homogeneous corresponding homogeneous system. So, here this minus 2 1 0 is added together with as a linear x3 multiplied by 5 minus 2 1. So, this will be the general solution of the non-homogeneous equation that you have considering, that is a particular solution you have to have. So, here this is minus 2 1 0 is a particular solution, and you have to add them as a linear combination of the free variable, and then the solution that you have obtained, general solution that you have obtained for the corresponding system of homogeneous equations. So, that is what I have written here. I have written this to be a general solution of the given non-homogeneous system of equations. Dear learners, we are at the end of the session. In this section, we learned how to express the linear system of the equation in a matrix equation Ax equal to b. Then we discussed the two types of matrix equation called homogeneous system and non-homogeneous system. By expressing the linear system in matrix equation, we learned how to solve the system also. I hope this module will be useful to you. We will see you again in the next module. Until then, thank you.